G'day, I'm Jacob Strickling and welcome to the Tiny Science Lab Chemistry course for ages 11 to 14. Now, you should have access to a chemistry set that looks something like this, or it could even look something like this. Either way, this is the equipment that you need to carry out this course. Now, this course follows the BBC KS3 Bitesize format. It would be a really great thing that not only that you work through the worksheets that have been provided from Tiny Science Lab, but that you also work through the interactives, the activities, the readings, and even the tests in the KS3 Bitesize. Now, before we get into it, the most important thing is your safety. Only ever do science practicals when there's a responsible adult to supervise. Otherwise, do not do any science experiments at all. You must always wear safety glasses when carrying out your experiments. If you have long hair or even medium-sized hair that can be tied back, please tie it back. Make sure you do it in a room that doesn't have too many or any flammables about, like curtains or paper or books. Do it in an open area where there's plenty of surfaces that are wipeable, and so that you won't damage surfaces like carpet or things like that. I'm looking forward to doing this Tiny Science Lab Chemistry course with you. Okay, in this first lesson, we're going to be lighting matches safely. Now, if you look at the matches, they say safety matches. That doesn't mean they're safe. In the old days, matches could be struck on any surface. You could strike a match on the table and it would light up. On the window it would light up. On your face it would light up. The matches lit up very easily. And sometimes the matches would sort of rub together in the boxes and spontaneously light, and they'd cause bad fires. So the makers got really clever. And what they did was they put some of the chemicals in the match head and some of the chemicals on the strike plate, so that you needed the two to work together to make the match ignite. Now, some key chemicals was red phosphorus and sulfur, and also potassium chlorate, which provides the oxygen. But they need a little bit of heat to ignite, and so that heat comes from something called friction. And if you rub your hands together, you can actually feel your hands getting really, really hot. Well, when you strike the match on the strike plate, there's actually powdered glass in the match head and powdered glass on the strike plate, and that rubbing is the friction, and that friction produces heat, and that changes the red phosphorus to white phosphorus. It's the same element, but different physical properties, and the white phosphorus actually ignites at a lower temperature, and so the white phosphorus ignites, and then there's potassium chloride for the oxygen, there's sulfur, and there's wood, and there's glue for the fuel, and so that's what causes the fire to keep going. So whenever we light our matches, we aim the strike plate at the middle of our heat-proof mat. So this is called a heat-proof mat, and it's made out of cement sheet, and it's not flammable, so it won't burn, which is great, because the wood is flammable, and so we don't want to put anything like a hot match on the wood, because it might burn it or damage it. So we aim the strike plate at the center of the almost forgot, I'm about to do a practical. I better put on my safety glasses. I better tie back my hair. Hello. Oh yes, there's a responsible adult who's supervising me. Oh, there's no flammable curtains or pieces of paper that can catch on fire. Fantastic. Now I can do this safely. So let's aim the match strike plate towards the center and we strike straight down. Look at that. Fire. We've got gases produced. We've got light given out. We've got heat given out. The wood is now gone dark, and so we're getting a new substance. Now these are all signs of a chemical reaction. Am I going to burn my fingers? Ah! Let's blow that out before I burn my fingers. If I did burn my fingers, I'd quickly go, I wouldn't run, I'd walk quickly to the nearest cold tap and I'd run my hand under cold water and then I'd seek some medical advice for how to treat it further. So, what were those signs of the chemical reaction? Let's put the burnt match on the heat-proof mat and let's light another match. What do? We aim the strike plate towards the center of the heat-proof mat. We strike straight down and then the match starts burning. And I get heat given out, which is energy. Light given out, which is energy. Gases are coming off. Wood is disappearing. Some type of black stuff is appearing. And these are all signs of a chemical reaction. There are new substances being produced as the atoms rearrange. The atoms break bonds and form new bonds, forming new chemical substances. Now let's do a little practical activity together. You will need your dissecting tweezers. Now with your dissecting tweezers, there's a little plastic tube, and with that tube, that's what holds it together to stop it going apart like that. So with that plastic tube, just put it back in the container where the tweezers were so that you don't lose it. Now, I'm going to need a stopwatch for this little activity. You could use a stopwatch like this, or you could even use one on your phone, and that's perfectly fine. And the question is, how long can we burn a match for? How long can we burn a match for? So, here we go. What I'm going to do, I'm going to get my match burning, and then I'm going to press the stopwatch. Maybe I need some help. Strike the match, start the timer, and I'm going to now hold it in my dissecting tweezers, and I want to try and burn it for as long as I possibly can. So I need to do some tilting and some twisting. I need to keep that flame going. Maybe, oh no! Oh, 21 seconds. That's how long I got to go for. I could do it 3 times. 3 times. I could add those 3 times together, divide by 3 to get an average, to see how long I can actually, or the average time for how long I can keep the match burning. So, that's how we light a match safely. Filling and using the Bunsen burner. Now this Bunsen burner is powered by butane, and the butane comes in a bottle that looks like this. Now it's a liquid under pressure, but it quickly converts to a gas, and then it actually can go back to a liquid again as well. Now to fill your Bunsen burner, you need to hold it upside down like this in a well-ventilated room. Even outside is terrific as well, but make sure the windows are open, or make sure you're not in a small room with the doors closed. It's got to be a large ventilated room, and you hold it vertically upside down. You grasp the butane can in your right hand and the Bunsen in your left hand, and all the other way around if you're left-handed, I guess. And then you push down right in the middle, right, just in the middle, and firmly, like this, and you should see the liquid transferring. Now there will be a little bit of gas that spills out, and it will feel cold, but that's okay. That's okay as long as there's not too much. And you don't have to fill it up all the way. You don't have to fill it up all the way. And so this Bunsen burner, is now it's a solid. It's a solid. There's a liquid and there's a gas on the inside as well. And so the pressure will push the gas up through the tube or the barrel of the Bunsen. Now, what we do now is we push it into our table. Now, I've got a larger table. You might have a smaller table, but it will do the same thing. Notice that there's a little lumpy thing here. That's called a key. And you have to find where the notch is so that the key goes into the notch. And then you push your Bunsen burner down, like so. Then, over the top of your Bunsen burner, you put your heat-proof mat. There we go. And that will help protect the table from any heat. Now, you'll put your hand under and you will rotate. You will rotate the bottom of the Bunsen burner. And when you rotate it, you should be able to hear some gas coming out. So, I'm rotating it, and now I can hear some gas coming out. If I open it up all the way, there's lots of gas. So I'm going to rotate it back, so now there's only a small sound coming out. So now I've only got some of the gas coming out. That's perfect. I put my safety goggles on, because I always do practicals with my safety goggles. I get my match. I aim it towards the strike plate, towards the middle of the heat-proof mat. I light my match. I wait till it's burning quite well, and then I bring it to the side of the Bunsen burner. There we go. I've lit the Bunsen burner from the side, and I will just lower the flame. There we go. I'll lower the flame like that. Look at that. Isn't that absolutely wonderful? But quite dangerous. Never put any part of your body over the top of the Bunsen burner, because maybe, oh, I just turned it off. Let's turn it back on. That's not a problem at all. Let's light it again. I light it from the side, and I blow my match out, and oh, I can get quite a strong flame there. That's quite energetic. That's very energetic. And if you put your hand over it or any part of your body, it will cause a burn. Now, it could be quite a serious burn. So the first thing you do if you burn yourself is put it under cold water, and then you seek urgent medical assistance. Thankfully, the responsible adult who is supervising you will be able to assist you. How good is that? That is exactly how we fill a Bunsen burner and we get a Bunsen burner going. Water from fire. Water from fire? Surely water puts out fire. Surely water can't come from fire. Well, we're going to have a look and show you that indeed it actually does. So here's a little beaker, our 10ml beaker. Now make sure it's dry. Make sure it's dry. This beaker is dry. And what I'm going to do is I'm going to just put some gas in the beaker, and then I'm going to light it with my match. So let's put it on the heat-proof mat, because it might get hot and we don't want it to damage the table. I'm going to pop on my safety glasses and make sure I'm in a well-ventilated room and that there's a responsible adult supervising me and there's no flammable things around. And I'm going to, well, you know what I might actually use as well? I might use the little resin plate as a lid, just to keep the gas in for a few moments. So, let's get the gas flowing. I'm actually going to close these two little holes with my fingers. They're air holes. I'm going to get the gas going, and I'm going to squirt the gas in. And 5, 4, 3, 2, 1. There we go. I'll put the little lid on. I'll put the Bunsen burner well out of the way. And then I'll light my match safely. And then let's, light the fire, or light the gas. And I can see it is burning. And can you notice that there's actually, it's gone a little bit misty in there. It has indeed, it's gone a little bit misty. There's been some water condensing. One of the products of burning butane is carbon dioxide gas, but another product of burning butane is actually water vapor. In fact, when you burn any hydrocarbon, even like petrol, water vapor is produced. And so on a cold day, when someone starts up their car, you'll see it's not white smoke coming out, it's actually like white fog or white cloud, and sometimes you can even see water driplets coming out of the back of the exhaust of a car, because one of the products of combustion of a hydrocarbon is water. Now, what about if we were to do it into this conical flask? It's a very small conical flask. Let's get the gas going. A little bit awkward here. Let's pop the gas in. The gas is flowing. I'll pop the lid on, turn off the gas, move the Bunsen burner away, and let's see what happens if we light it this time. What's your prediction? Ooh, I've got a little tiny flame, but it goes out pretty quickly. Ooh, I actually get some smoke going down there. Ooh, I get some beautiful smoke happening there, but no real fire. Do you know why you don't get any fire when you've got the conical flask? Do you know what fire or the hydrocarbon needs to burn? Something in the air. It makes up 20% of the air, or about 1/5 of the air. Did you say oxygen? Absolutely. And the problem is, with the very narrow neck, not very much oxygen can get down and actually react with that hydrocarbon, the butane. And so because it's missing a reactant, because it's missing oxygen, the hydrocarbon does not burn. Oh, and that reminds me of something else that we can look at. How about we put the Bunsen burner in the table, put the heat-proof mat on. I'm going to light my match, and I'm going to light my Bunsen burner, and I get a beautiful blue flame. I'm getting what's called complete combustion. Now remember I said that the butane requires oxygen to burn? Well, yes, it can get some oxygen from the top, but most of the oxygen is actually coming in through these little tiny holes there. There's little tiny air holes. And let's have a look, see what happens if we block those holes. Now be careful that you don't put your fingers near the flame. And I'm just going to block the holes, and look at that. Whoa! Oh! I get incomplete combustion, and an orange flame. That's actually not very hot at all. The orange flame is not very hot at all. Okay, we're going to do an experiment to find the hottest part of the flame. Now, let's light the Bunsen burner. I will make sure I've got my safety glasses on and my hair tied back, and that there's a responsible adult and I'm in a well-ventilated room. And I will strike the match down, and I will turn on the gas, and I will light the Bunsen burner. And if you have a close look at the Bunsen burner, there's a nice blue cone in the middle, but then there's a bit of a lighter colour on top. It's a larger cone, but it's not as intense. And you've got the bottom of the cone. So I'm going to say that there's 3 distinct places in this flame. There's the very, very top of the flame. There's the top of the inner cone. And then there's the bottom of the bottom cone. Now, I wonder which part or which zone is the hottest. Well, to find out, we can do an experiment. And so I'm going to use a stopwatch. You can use a stopwatch like this, or one that's on your phone or iPad or computer. I'm going to need my dissecting tweezers, and I'm going to need my wire gauze. Okay, so there's a wire gauze that looks like this. It's a wire gauze. Now, I'm going to hold it. I'm going to hold it first in zone 1, which is the very, very top of the flame. And so, are we ready? I'm going to hold it at the very top of the flame, and when it glows orange, I'm going to stop the stopwatch. So, I need to make sure that the flame is consistent. So I'm quite happy with that. And ready, set, go. So timing, 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 and it's glowing orange. Bing, there. So 5.25 seconds. Now, what do you think I'm doing here? Fanning myself? Just trying to keep myself cool? No, I'm trying to return the temperature of the wire gauze to the same temperature that it was at the beginning. I need to have everything the same for this experiment except for one thing, and the thing that we're going to change is which zone we're holding it in. So what we do now is we hold it in the same zone a second time. And, ready, make sure it's the same. Yes, it's back to room temperature. Ready, set, go. Okay, timing, timing, it's going orange, and boom. Ooh, 4.95 seconds. So I write that down and I find the average. Now you do it for your Bunsen burner, because you'll get similar but slightly different results because your flame might be different than mine. Now I'm going to do the top of the inner cone. Ready? Or better cool it down. Is it cooled down? I think so. It's not a good idea to touch it because it still might be hot and you might burn yourself. Okay, here we go. Ready, set, go. Holding in the top of the... and boom. 3.9 seconds. That was faster. The time went quicker. Probably means that that zone above the inner cone is hotter than the top of the flame. That's interesting, isn't it? Wave it around, cool it down, and ready, set, go. And action. 3.94 seconds. Okay, so let's write that down and then you can calculate the average by adding the two values up and dividing by 2. To find an average, you add up the numbers and you divide it by how many numbers there are. Now the third one, and this is what's called a quantitative experiment. We're actually taking values and numbers. Are we ready? Reset the stopwatch. Set. I'm going to do zone 3, the bottom of the flame. And starting. Ooh. And ready, set, stop. 5.5 seconds. Ooh. That seemed to take the longest. Just by a little bit. Just by a little bit. But it definitely took the longest. And let's do it once more. And ready, set, go. Oh yeah, you can definitely see that it's taking a longer time. And ready, set, stop. 6.2 seconds. So, look at that. That took the longest time. And so the hottest part is zone 2. Then the next hottest is zone 1. And then the final one is zone 3. How good's that? Now going to be looking at the chemistry of honeycomb. Now, we don't actually need honeycomb. Okay, we're going to be looking at the chemistry of honeycomb. Now, we don't actually need honeycomb, but what we do need is the little aluminium pan, and we need a couple of tiny spoons of sugar crystals. Okay, so white sugar crystals are the best for this. We don't want too many of them, but we do need a couple of spoons of sugar crystals on the little aluminium pan. We also need your sodium hydrogen carbonate. Now, sodium hydrogen carbonate, the common name is actually bicarb soda. And you really only need the smallest amount. I'm talking like half a tiny little spoon. Really not much at all. So let's now light our Bunsen burner because we need a little bit of heat to activate this chemical reaction. So let's light the Bunsen burner, rotate it so that we've got some gas. Perfect. Put my hot match on the heat-proof mat, and of course you need to have your safety glasses on and your hair tied back before you light the Bunsen burner. Now, I'm going to get the tripod and the wire gauze. Now, the tripod and the wire gauze will both get very, very hot. They might not look hot, but they will get hot, and if you touch them while they're hot, you could burn yourself, and if you do, then you need to run it under cold water and seek some medical advice. Now, I've also got a little wooden spatula. Now, if you don't have that, you could actually use the glass stirring rod, and I'm going to also use my dissecting tweezers to hold my little aluminium pan. Now, many people will do the wrong thing and burn. They'll overcook their sugar. Now, we only want gentle heat, and we want to try and move the sugar around a little bit as it's heating up. Now, as it heats up, we'll undergo firstly a physical change. A physical change will firstly happen. That is that the sugar will go from a solid to a liquid. That's a physical change. That's a change of state. And so it's sort of happening now already, and it's starting to go a bit golden, which means it's actually sort of like almost undergoing a chemical reaction. I'm going to put the plate there, and then I'm going to pop in a little bit of the bicarb soda, and then I'm going to stir the bicarb soda through, and what will happen is it will start frothing up a little bit. Oh, it did cool down a little bit, so I might try and cheat a little bit and try and get a little bit of heat happening again. Maybe I can activate that bicarb soda, the sodium hydrogen carbonate. I think I can. It is starting to go a little bit frothy. Ah, look. Yes. Look, it's frothing up. Yay! It's frothing up. Now, I know it's very tempting to taste that, but you should never taste really anything in science unless you can be 100% sure that your equipment is free of any chemicals. And you can't guarantee that with this equipment. So my suggestion is that if you want to make some honeycomb that you can eat, then you actually use a fry pan and some sugar in the kitchen and some bicarb in the kitchen. And don't taste the chemical or the honeycomb that's been made on the chemicals from your science equipment. Now, when the bicarb heats up, it undergoes a decomposition reaction. It actually breaks down into one of the products that is produced is actually a gas, carbon dioxide gas. Isn't that amazing? Carbon dioxide gas. So good. We're now going to be looking at the density of carbon dioxide gas. Now I've got two large containers here, a glass and a glass, and I need a little birthday candle, which I'm going to light. So let's light the candle. Oh, happy birthday to me. And I'm going to drip some of that wax into the glass. Now, wax is quite troublesome to clean off things, so maybe don't use like the best glass that you can find, because you might get in trouble. So I'm going to drip the wax in and then blow out my candle and then stand it upwards, ow, in the glass so that it's glued nicely to the bottom of the glass. And that's a physical change as the liquid wax solidifies. It freezes. The wax freezes. Hey, look at that. It's a magic trick. So I'm going to pop in there on the heat-proof mat. And then I need some, well, I might put some bicarb soda in this glass like this. So pop that in. Lots of bicarb soda. And then I'm going to light my candle again. Get the candle burning. Oh, it's quite pretty, isn't it? And so oxygen gas is actually coming in and combusting with the gaseous wax. Now, some people think that candles, that the wick is what sort of burns and that the candle wax is just there to support the wick, but that's not actually the case. The wick goes down into the candle, the solid candle, but the heat from the flame melts the wax, and then that liquid wax travels up the wick, and then it heats up even further, turns into gas, and then the gas ignites. So here's a little trick that you could try. Let's see if I can do this trick. Blow out the candle, and then bring the... Woo! Did you see the flame jump? Let's try that again. Oh! Let's try that again, hey? So, let's try this trick. Get the flame burning. Oh, blew out the wrong one. And then... Oh! Did you see the jump? Let's try that again. Woo! See how the flame jumps down? That's because the flame ignites the gas coming off the candle. Now, when I put vinegar with the bicarb soda, we're going to get a chemical reaction, and one of the products is carbon dioxide. Whoa, 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 whoa. That was a bit too much. But I'm now going to pour. Oh yeah, wow, that didn't quite work. So let's try again. Bit more vinegar. And whoa! I'm putting in too much. That's the problem. Let's try pouring just the gas. Oh. Let's try once more. Pour. Yay! I poured the invisible carbon dioxide gas into the glass, and because the carbon dioxide is quite dense, it sinks down and then it starts rising as I keep filling it up until it covers the candle, and then the flame goes out. The density of carbon dioxide gas is greater than the air around us. There we go. Do you know what this is? It's a yellow... Do you know what this is? It's a yellow solid. It's made up of the one type of atom, so therefore it is an element. It's found in volcanic regions. It ignites, it burns relatively easily, and it burns with a blue flame, and it puts out a toxic gas. And in the Bible, when it talks about burning brimstone, this is it. Its symbol is S, and of course it's found on the periodic table, and it's sulfur. That's some sulfur, and here is some powdered sulfur. Now, this activity is just a demonstration only. I doubt that you'll be carrying out this one. If you do happen to carry it out, make sure you do it in an open space, and make sure, if it's not in an open space, that's done in a fume cupboard. This is a bottle of powdered iron, so otherwise known as, iron filings. Look at that, black iron filings. And iron has got the property that it is magnetic. Look at that. Can you see how the iron filings are now stuck to the end of this magnet? And I'm asking myself, how am I going to get them off? Might try and peel them off a little bit. Ugh, well, that didn't work so well. Maybe I should have put some cling wrap around my magnet. Okay, so I'm going to put some of that, let's make a mixture. I'm going to make a mixture. I'm going to mix the two. I might do it in a beaker actually. I'm going to mix some of the iron filings. So let's get some of the iron filings. 1, 2 spoons. And some of the sulfur. 1, 2 spoons. And I'm going to give them a bit of a mix. So I've now got a mixture of iron filings and sulfur. And I could probably separate them using the magnet, but I actually want to do a chemical reaction. And so I'm going to now tip that mixture of iron filings and sulfur into the test tube, and pop on my safety glasses, and I'm going to need heat to cause this chemical reaction to occur. And so I'm going to use the Bunsen burner for the heat, and I'm going to hold my test tube with the... Oh, it went out. Oh, I just tipped it out. Oh no, what am I doing? I'm not very good at this game. You're probably thinking, Mr. Strickling, let's get the gas going again. Whoa, that's better. So, let's heat up this mixture of sulfur and iron filings. Now notice that I'm not pointing it towards me. I'm not pointing it towards anybody actually, because you never really know what's going to happen when it heats up. It might go shooting out. But in actual fact, I can actually see some yellow gas. Some yellow gas. That's actually the sulfur, which is evaporating. Now, whoa, I've got some sulfur gas coming out there. Oh, whoa, 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 whoa. I can't believe that my teacher let me do this in year 7. Mrs. Rockwell. So, anyway, let's keep heating this up. Now, that is quite toxic. That's quite toxic. And that's why you need to do this experiment in a fume cupboard or outside. So, very toxic indeed. And probably start smelling a bit like a volcano around here. Sulfur is actually hugely important to, well, hugely important to, let me just see if I can smell it. I'm sort of wafting it towards me a little bit, and it smells, smells like a volcano. Not that I've ever been to a volcano, but it actually smells like New Zealand hot springs, because there's a lot of sulfur that's brought up with geothermal activity, and the reaction that occurs is that the iron and the sulfur react to form iron sulfide. That's the chemical reaction that should be occurring. Now, how do we test to see whether indeed it has happened or not? Has this reaction gone to completion? Well, whoa! It's glowing quite red in there. Can you see how it's glowing red there? And when we heat the mixture, we should always keep it moving around. But look at that. You can see the glow. And I'm quite sure that if I tip this out, there we go. I've got some. Whoa! Uh-oh! Look at that. There's the blue flame I was talking about. You can just see a little blue flame. But I'm going to see if a chemical reaction has occurred by bringing in the magnet, and it's still magnetic and it's still burning. So in actual fact, I haven't actually produced iron sulfide, but I have given it a good go. And obviously I needed to heat it up for a bit longer. I hope that you've enjoyed this first part of the course, Introduction to Chemical Reactions. Bye for now.